In AS Maths, you will have come across binomial expansion as a method to help us with expanding brackets that have really high powers, making it not worth our while trying to do them completely by hand. So this could be a bracket to the power of 10 or so forth. Yet what would you do if you instead had brackets that either had a negative power or a fractional power? Because the problem is, with the usual binomial expansion method, you'd be minusing one from the power or adding one to the power until one of them became 0. Yet here, if you're already starting with a negative power and you're minusing, you're not going to reach 0 that way. And similarly with a fraction, you're not actually going to land on 0 itself. So we're going to need a slightly adapted form of this formula. So again, just to make it clear, if you aren't as familiar with the AS binomial expansion, I would strongly suggest that you go over that first, because here we're going to be focusing more on what's different, what's new, rather than going over everything from scratch. Okay, so let's say that you had a bracket which was 1 plus ax to the power of n, where n is going to be either a negative or a fractional power. What we can say is this would be approximately the same as 1 plus and then n over 1 factorial. So factorial saying basically times every integer beneath it until you reach 1. It is on your calculator, you may just have to find it depending on the model. So n over 1 factorial, and then that would be ax to the power of 1. You need to add to this n times n minus 1. So if you say you started with n being minus 2, you'd now times that by minus 3. If you'd started with a half, you'd now times minus a half. And that will now be over 2 factorial. And you times that by your ax squared, and so forth. The next term would be n times n minus 1 times n minus 2 over 3 factorial. And that would be times ax cubed. And this one wouldn't stop, this one would keep on going and going, but as with the AS questions, you would just be asked to do like the first 3 terms or something like that to give an approximation. So another part of this, as well as it having to be a negative or fractional power, is that this first term here has to be 1 this time. So if instead you had something that was more like b plus cx to the power of n, where b is not 1, what you'll have to say first of all is that this would be the same as if we took out b as a factor and then kept that as a power of n, then inside b divided by b is now going to be that 1 that we need. And then here this would simply just be the c over b, x to the power of n. So if your first term is not a 1, factorize it out, but then don't forget to put the power on it as well, and that will be 1 plus, and then whatever this coefficient was, divided by that, x, so that same power as before. And for one final thing before we get into an example, specifically here, there are conditions under which this works, right? This only works if the modulus of x, so if you were to ignore whether it's a plus or minus, just the value of x is less than b divided by c. So before you've done any of your like factorizing whatever here, the x value would have to be less than this number on its own divided by that x's coefficient. If it's not, then we would say the expansion isn't valid. Okay? So with these kind of established, let's just have a go at putting them into practice. So to begin with, we have expand 1 plus 3x all to the power of a quarter up to the x cubed term. Well, to start off with, first term is always 1. Then we'll add on to that, so our n is a quarter, and divide that by 1 factorial, and we'll times that by our 3x. Then add on to that, a quarter times, and a quarter minus 1 is minus 3 quarters, and that's then over 2 factorial, and then that will be times by 3x squared. And then finally, because we're just going up to the x cubed term, so a quarter times minus 3 over 4 times minus 7 over 4, because that's minusing 1 again, all over 3 factorial, and then you'll times that by 3x cubed, and that would continue, but we're not interested in those higher values. To then simply just put these into your calculator, so obviously 1 is still going to be 1, but then a quarter over 1 factorial times 3, that will get you 3/4 x. Then here, quarter times minus 3/4 over 2 factorial times 3 squared. That's going to leave you with minus 27 over 32x squared. Then finally, this fraction here times by the 3 cubed, that's going to get you 189 over 128x cubed. And again, the expansion would otherwise continue. Well, now that we have this expansion, we could then be asked to approximate, in this case, the fourth root of 1.03. Well, the fourth root is the same as the power of a quarter, so we've already got that the same. So it's now a matter of saying, okay, if we could find an x value that would make the contents of this bracket the same as 1.03, we could then substitute that into our expansion to get our approximation of it. Well, obviously we've already got our 1 here, so we don't have to worry about that. So the 3x just has to account for 0.03. So dividing by 3, we therefore have that x is going to equal 0.01. If we just want to double check, our x being less than 1 divided by 3, so less than a third, yep, that's definitely less than a third. So to substitute this into our expansion, it'll become 1 plus 3/4 of 0.01 minus 27 over 32, lots of 0.01 squared, plus 189 over 128, 0.01 cubed, and this would get you a value that is approximately 1.0074. Actually, if you were just to also put your fourth root of 1.03 into your calculator as is, you would find this is practically the same. These first 4 decimal places are the same. It's just a matter of going after that it changes. But on that level, is it really that significant? With that established, therefore, could you have a go at just doing an example of your own? So, if you had 1 minus x to the power of minus 5, to expand that once again up to the x cubed term. As I've said, throughout any expansion of this nature, you're going to be using the exact same formula, the exact same structure. All you have to do is just identify, first of all, what is your a and what is your n, and plug them in the appropriate places. So, pause the video, have a go for yourself, and then press play again when you're ready to compare. So, as always with this kind of expansion, your first term, regardless, is just going to be at 1. Then for your second term, so we'll add on to this, your power, your n, is minus 5, and that will then be put over 1 factorial. And this will be times by minus x, just on its own for that first term. Next, we'll then add the minus 5. That's then times by, in this case, minus 6, because minus 6 is 1 less than the minus 5, the original power. That will then be put over your 2 factorial. You times that by minus x squared. For our final term, because we're only going up to x cubed, we have minus 5 times minus 6, now times minus 7, because again that's 1 less, over 3 factorial, and times that by minus x cubed. To expand this, therefore, well, 1 is still just going to be 1. The minus 5 times by minus x, that's just going to leave you with a plus 5x, because minus times minus is a plus. In this case, this second term is just going to come to plus 15x squared, and the third term would come to plus 35x cubed. In all the cases, you end up with all of the minuses cancelling out with each other, whether that's from the fraction itself or in combination with the negatives that may remain from your x term. Okay. Well, if we had that, then what might we do if instead we had been told to expand, so the fourth root of 1 plus 3x over 1 minus x to the power of 5 up to the x cubed term? Well, this, if we may spot, is just the combination of these previous 2 expansions. The fourth root of 1 plus 3x is just 1 plus 3x to the power of a quarter, and dividing by 1 minus x to the power of 5 is the same as 1 minus x to the power of minus 5. So if you wanted, you could basically write this as just this bracket here times this bracket here, or because we already have the expansions, we can say that this would be our 1 plus 3/4 x minus 27 over 32 x squared plus 189 over 128 x cubed times by 1 plus 5x plus 15x squared plus 35x cubed. Now, to times these all out would lead to a number of terms. However, we do have a slight shortcut in that we only need to go up to x cubed. Certain powers times together would give us a value that's greater than that, so we don't have to worry about those. So to just expand and again demonstrate just what I mean by that, if we were just to times each term by each term, so first of all, to times this entire bracket by 1 would just be to repeat the bracket again. So 1 plus your 5x plus your 15x squared plus 35x cubed. But then to do the bracket times by 3/4 x, well, that will be 3/4 x plus 15 over 4x squared plus 45 over 4x cubed. Oh, we've already reached our x cubed term. We're not going to times the 3/4 x by the 35x cubed as well, because that will get us to the power of 4. That's higher than we need to expand to. So we can now just shift straight to the next term times by the bracket. So minus 27 over 32 x squared minus 135 over 32 x cubed. Oh, we've already reached the cubed term. To times the 27 over 32x squared with 15x squared or the 35x cubed will get us powers that are too high. Don't want them, don't need them, we can move on. But here now, all we're going to have is the 189 over 128x cubed times by the 1, because to times by any other term with an x in, again, takes the power too high. So we'll just add that on the end of our current expansion. To then just simplify these, collect together like terms, the only term without an x is 1. Again, the expansion is always just going to begin with 1. You may want to cross these off or tick these off just to keep track, make sure you've accounted for all the ones you need to. If we're now looking at just terms with a single x power, that's 5x plus the 3/4 x. So together that would make 23 over 4x. I can now cross those off. For the x squared terms, you've got 15x squared plus 15 over 4x squared minus 27 over 32x squared. This altogether gets you 573 over 32x squared. Take off those terms. And then lastly, we've got these 4x cubed terms here, which, if you combine them, gets to 5,569 over 128x cubed. So as you can see, with these expansions, the fractions can get big quite quickly, but that's just because of how precise we're being. If you were to get that as a decimal, that, I mean, it's still like obviously bigger than 1, but it's more reasonable number from expansion you would expect with these powers. Okay, so that's just showing that a question may get you to do some parts of expansion individually, but then as latter parts then get you to combine those together, in which case, yeah, you would just times out your brackets. Potentially also if they had given you some unknowns in like a second expansion to then just times by a single one that you've done, and told you what the coefficients are meant to be at the end, you could then do that technique of comparing coefficients. So expand it out algebraically as best you can, and then say, okay, this is what I have for the x squared. They've told me I'm meant to get this for x squared, so therefore I can work out what that missing letter is. Well, with that in mind, let's just have a look at a few other variations of these questions. So, show that the first 3 terms of the expansion, so of fx equals 6 over 2 plus 3x minus 4 over 3 minus 5x, can be written as 5/3 minus 121 over 18x plus 329 over 108x squared. In this case, we're going to now have another instance of combining 2 expansions together, only this time we're going to be minusing them rather than timesing. So to start off with, if we were just to rewrite these fractions in a form that's more obviously for the binomial expansion, this would be 6 and times 2 plus 3x to the power of minus 1, and then minus 4 lots of 3 minus 5x to the power of minus 1. However, this is now where we get to what I was suggesting before, that for this kind of binomial expansion to work with either a fraction or a negative power, the first term in the bracket wants to be 1, which is not the case in either of these. So we're going to need to factorise out whatever non-1 number that is in each case. So for the first bracket, I'm going to still have 6, but then we'll factorise out the 2, not forgetting to still keep it to that power of minus 1, and that will leave the bracket being 1 plus 3 over 2x to the power of minus 1. Then here, still have the 4, now factorise out that 3 to the minus 1, and then times that by what's left, which is the 1 minus 5 over 3x to the minus 1. To expand these now, so 6 times 2 to the minus 1, that's the same as 3. So there's 3 lots of this expansion just up to the x squared term. So that expansion will be 1 plus, and then the minus 1 over 1 factorial, times by your 3 over 2 x. Then add to that your minus 1, now times minus 2, because that's 1 less, over 2 factorial. Then times that by your 3 over 2x squared. Close off that bracket. And now 4 times 3 to the minus 1 is 4/3, so minus 4/3 of, in the big brackets, 1 plus minus 1 over 1 factorial times by minus 5 over 3x. Then add to that minus 1 times minus 2 over 2 factorial over minus 5 over 3 x squared. Close bracket. From this point, if we were just expand these out in terms of each individual square brackets first and then combine them together, 3 times all of this should leave you with 3 minus 9 over 2x plus 27 over 4x squared. And then minus this bracket, we should end up with minus 4 over 3 minus 20 over 9x minus 100 over 27x squared. So then just collecting together the like terms, that would simplify to the 5 over 3 minus 121 over 18x plus 329 over 108x squared that we had to show. Now, once we have this expansion, we can use it to find what is called the percentage error. So find the percentage error of this expansion for f of 0.01. So it's basically saying if we were to work out what the actual value for this equation, these fractions, where x is 0.01, and then compare that to what answer we get from our expansion here for 0.01, how different is it? Well, to start off with, we'll therefore need to work out what values we get from this. So if you were just to do your f of 0.01, we'd be saying that you're doing 6 over 2 plus 3 lots of 0.01, and then minus 4 over 3 minus 5 lots of 0.01, which, if you were to actually just write out everything on your calculator screen this time, just to be as accurate as possible, you'll get 1.59973281. Then, as you're putting it into your expansion instead, you would have 5/3 minus 121 over 18 lots of your 0.01 plus 329 over 108 lots of 0.01 squared. This is going to equal then 1.59974907. So once again, we may see the reason why I specified writing out everything in your calculator is already it takes up until the 5th decimal place, once again actually, in order for any difference to be noticed. In order to get the percentage error of this though, we're going to need to get the difference between these two numbers divided by the actual number. So here we're going to have 1.5997. We'll go with the bigger one minus the smaller one. So 490 1.59974 minus 1.599732821 all over that other one, so the 1.599732821 times by 100, and this gets us a percentage error of 0.001%. This expansion, at least for when the x value is 0.01, is 1/1000th of a percentage off from the actual value. Again, just going to show how accurate these expansions can be, so long as the x is conforming to the parameters for which this works. Again, that being that the modulus of x is less than, or in the first bracket would have been 2 divided by 3, or in the second one, 3 divided by 5. So that's how we can deal with multiple expansions if we then just have to add or minus them, and again how we can adjust the brackets so that they both begin with 1. But what if instead we wanted to tie in another topic from maths, that being partial fractions? If you haven't covered partial fractions yet, I would suggest that you do for context for this, but of course I will go through the steps anyway as part of this question. So given that, so 4x squared minus 4x minus 9 all over, first bracket 2x plus 1, and then another bracket x minus 1. Given that that is mathematically the same as a plus b over 2x plus 1 plus c over x minus 1, where a, b, and c are going to be constants to be found, find an expression as far as the x squared term, or the expansion as far as the x squared term. Just like we had with the fractions here before, in order to expand them, we'll need to rewrite them in a form of a coefficient and then a bracket to a power. But in this case, because we have two brackets within the same denominator, we'll have to split them up first, and that's why turning them into partial fractions is going to be helpful. They've specified in this question that they do want them in 3 terms, where the first term would just be a number on its own. So we're going to make it into that format, because again, that's how I make it fit. The first step with your partial fractions is that you'll times up by both of the brackets in the denominator, leaving you with just the 4x squared minus 4x minus 9 on the left-hand side. Then on the right-hand side, that'll end up with your a being times by both brackets. Meanwhile, your b is only going to be left being times by the x minus 1, because timesing by the 2x plus 1 is going to cancel with that 2x plus 1. So b lots of x minus 1. And then similarly, c is just going to be left being times by the 2x plus 1, because the x minus 1 bracket is already going to be cancelled with it as the denominator of that fraction. If we were to now pick x values that will make some of these brackets disappear, let's say we would pick x equals 1. Substituting x equals 1 into the left-hand side, that's just going to leave us with minus 9. Here, 1 minus 1 is going to be 0, so because these other terms being times by 0, doesn't matter what they are, they'll disappear. Same with the b term, 1 minus 1 is 0, makes b disappear. So what we're left with is 2 times 1 is 2, add 1 is 3, so that's 3c. Therefore, you can say that c is going to equal minus 3. To get rid of the other bracket, we'd have to say that x equals minus a half. So to do that, substituting minus a half into here leaves you with minus 6. That will equal, once again, this a term is going to disappear now because the other bracket is going to end up equaling 0. Here, minus a half minus another 1 is minus 3 over 2, b, and again, this bracket will make this c disappear. Therefore, we can work out that b is going to be 4 by just dividing over the minus 3 over 2. Lastly, to work out a, because it's times by both brackets, we can't use the technique of eliminating a bracket. So once we know b and c, we can now just substitute in any other x value and solve for that. So let's just go with an easy one, which would be x equals 0. If x equals 0, the left-hand side, once again, is going to equal minus 9. And here, 2 times 0 is 0, add 1 is 1, 0 minus 1 is minus 1. So 1 times minus 1 is minus 1, making this minus a. Then here, 0 minus 1 is minus 1. So minus 1 times b, which we know to have a value of 4, will make that minus 4. Then here, 2 times 0 is 0, add 1 is 1, so just one lot of c, but c was minus 3. So just rearranging this, so you'd add the a onto the left-hand side, add the 9 onto the right-hand side, you end up with a equaling 2. So from our original expressions then, what we can say is that instead of our a, we are going to have 2 here. Instead of our b, we're going to have that 4. And instead of a plus c, we're now going to have minus 3. Turning these into the binomial expansion form, well, the 2 is just going to remain 2, but now that will be plus 4 lots of, and because it's addition, it doesn't matter which way around you write it. I'm just now going to put the 1 first, and then plus 2x to put it in a more binomial expansion form, because 1 plus 2x is the same as 2x plus 1, that's the minus 1. Then here, you'll have minus 3 lots of x minus 1 to the minus 1. Now, while this is a 1 here, it's a minus 1, and that's not good enough. It has to be a positive 1. So, we're going to have to take out a factor of minus 1 in this case. So you can just say this will be the same as 2 plus, again, that 4 plus, lots of 1 plus 2x to the power of minus 1. But now minus 3 times by minus 1 to the power of minus 1. If you take out a factor of minus 1, the minus 1 will now become positive 1. The x will become a minus x, again still to that minus 1. And what we can say here, that minus 3 times minus 1 to the power of minus 1, that's going to be the same as if we just had a coefficient of plus 3. So now, if we were to expand these, 2, obviously still just a 2, but now we're going to have 4 lots of, and because we're just going up to the x squared term, like last time, we just need to do the first 3 terms. So 1 plus minus 1 over 1 factorial times by your 2x, then add your minus 1 times by minus 2 over 2 factorial times by your 2x squared. Now add to that 3 lots of 1 plus minus 1 over 1 factorial times by minus x, and then plus minus 1 times minus 2 over 2 factorial times by minus x squared. To now expand and simplify this bracket, again as we have done before, you would end up with 2 plus 4 minus 8x plus 16x squared, and then plus 3 plus x plus 3x squared. All of these end up balancing out to just all have coefficients of 3. So to then just bring together the like terms, your 2 plus 4 plus 3, that's going to leave you with 9. And then minus 8x plus 3x is minus 5x. And then plus 16x squared plus 3x squared makes for plus 19x squared at the end. Then just to round off, why is the expansion not valid for x equals 3/4? And if we think back to the parameters for x as to what makes this expansion valid, well, the modulus of x has to be less than, in what was the algebraic example I gave above in the first screen, b over c. In this case, if we look at the 2 brackets that we were expanding algebraically, from this one here, we would have to have that the modulus of x is less than 1 over 2. And technically you also have that the modulus of x is less than 1 over 1 from this one, but this is the smaller value that we have to be less than, so this is the one we'll focus on. So the modulus of x has to be less than a half, but 3/4 is greater than a half. Therefore, it is not a valid value of x for this to work.